Imagine that you're the manager of a hospital facility treating patients for a single disease. Your initial treatment plan is to administer 3 shots of the cure to each new patient that arrives at the facility each day. Now, your treatment plan will be used on a list of patients each day that they visit. The schedule starting out as 1 person visiting on Monday, 2 people on Tuesday, 3 on Wednesday, all the way up to 5 people on Friday. How much medicine will we need for the week? A simple multiplication reveals that on Monday we'll need 3 shots, Tuesday 6, etc. And if we add up all the total number of shots, we have 45 shots needed for the week. But what happens if, let's say, the disease mutates and we need a more aggressive treatment? So we devise a new plan. We're going to administer 3 shots on day 1, 2 shots on day 2, and 1 shot on day 3 with the same patient schedule. But now a simple multiplication won't do the trick. How will we figure out the correct amount of medicine for each day and in total? To understand the logistics of this nightmare, we're going to have to really work it out brute force. So here's a suggested patient list. We'll use A for Allison, B for Bob, C for Carla, D for Dave, and so on. Now, on Monday, we'll start off with Allison. Allison will get her 3 shots, and that's the only person since only 1 person visits on Monday. Then next we have both Bob and Carla getting their 3 shots, Allison coming in for her second shot, her second day of 2 shots. On Wednesday, 3 new patients get their 3 shots, and the people who were there previously get 2, and so on. And here's the schedule for Thursday, followed up by our schedule finally for Friday. And once we get to Friday, we'll have to add up all the total amount of medicine used. So we'll have to add up all the shots here. Now that's a pretty daunting task. Can we not organize the lists that we had earlier in a way in which we can combine them to get the results that we need? And the answer to that is yes, with an operation called convolution. And we'll use a star here to indicate that operation. And so here would be the results of what we just explored in our convolution. We would want the result to be 3, 8, 14, 20, and 26. So how might we organize those lists and use a convolution to do this? Well, if we start out by looking at our 2 lists here and take the patient list and reflect it to the other side, then translate it across for a desired day. Let's say for Tuesday, we translate it over 2 days. We multiply the numbers in each column and then add the results. And that gives us the result for Tuesday. And so it is a reflection and a translation that is ultimately taking place to have the 2 lists interact with each other and basically multiply and accumulate the results. We have convoluted the results because it is a more complex way of combining the items. Now, if we were talking about general functions like f of x and g of x representing the treatment plan and the patient list, then a horizontal reflection would be g of negative x, and then a translation to the right might be g of t minus x. And we're going to see that this notation is going to play a role in the definition of a convolution integral. The integral from negative infinity to positive infinity, where we take the function f and use a new variable here, u, and then g of t minus u integrated with respect to u. And this has a lot to do with signal theory, and there's some really good videos out there if you want that explore how this is involved with signal processing and image processing. But for now, we're going to focus on this little more mathematical application to convolutions. And if we were working on the interval from 0 to infinity, we can define the convolution integral from 0 to t in this way and define a function of t. So now that we have an idea of what this integral is defined to be, we're going to look at some of the properties that come along with it. Namely, one of them is that convolutions are commutative, and they have this property here that the integral of the convolution of f with g is equal to the product of the separate integrals. Let's do an example to really take or drive home this idea of what a convolution does. For our first example, we'll do the convolution of a function f with the constant function 1. So let's take f to be the function t squared and g to be the function 1, and we'll calculate the convolution. Since convolution is commutative on the interval from 0 to infinity, we get the convolution to produce the function t cubed over 3. Now, the integrals are not terribly difficult to do, and sometimes using the commutativity property that you can switch the order of g and f makes doing these integrals very nice. So the next one we're going to look at is if we have a function f of t equal cosine t and g of t equal to the same thing. So convoluting a function with itself. And here, using the example of cosine and plugging in a little identity for cosine of t minus u into this integral, we can write it in a nicer form and then evaluate both pieces. And here we get t cosine t plus sine of t all over 2. And that is when we convoluted f cosine of t with itself. So there's some interesting properties and some interesting applications of convolutions that we'll be specifically interested in. A very compelling formula involving convolutions is the fact that you can take the Laplace transform of a convolution of functions and it'll be equal to the product of the Laplace transform of those functions respectively. And this could also be applied to Fourier transforms as well. Now, the application to solving differential equations using a Laplace transform is something I'm going to go over now. And if we imagine that we used a Laplace transform to solve a differential equation and got this as our answer, capital Y of s is equal to a over s squared times s squared plus a squared, we would be required to use an inverse Laplace transform to compute the solution to that differential equation. So the inverse Laplace transform of a over s squared times s squared plus a squared. And how do you find that? Well, we could try to process that through a series of partial fraction decompositions, but we might observe that we can split this particular expression into the product of two things, 1 over s squared and a over s squared plus a squared. And if you're familiar with Laplace transforms, you might be familiar with the fact that the Laplace transform of t is 1 over s squared, and the Laplace transform of sine of at is a over s squared plus a squared. So we can use those facts in there to sort of play around with that expression. So if I took the inverse Laplace transform of both sides of that expression, the right-hand side would have me calculating the inverse Laplace transform of the product of 1 over s squared and a over s squared plus a squared. But we know that that's not going to be equal to the product of the inverse Laplace transform separately. But because of the fact that we can use a convolution to solve this, the inverse Laplace transform of that product in there can be replaced with the inverse Laplace transform of the Laplace transform of the convolution, which is just the convolution. And so calculating that integral, again not that terrible, is at minus sine at over a squared. So a very useful technique in solving differential equations. Now consider the differential equation y double prime plus 3y equals g of t with the given initial conditions, similar to a problem that I solved in my last video. Now, since we don't have a function g of t explicitly given, when we take the Laplace transform of both sides of this equation to try to solve it and use linearity to split up the pieces on the left-hand side, we're still left with trying to find the Laplace transform of the function on the right-hand side. So we'll just use a capital G of s to represent that. And then we'll also represent the Laplace transforms for y double prime and y prime in here. And then we can manipulate this and isolate that y of s expression, and ultimately we'll get this rational expression, which we could break up into 3 pieces. And thus, when we go to take the inverse Laplace transform of this equation, the pieces are easy enough until we get to that last piece. So the first term in that expression will give us a cosine of at, and we can deduce that the a is going to be the square root of 3. So that's for the s over s squared plus 3 term. And then for the 1 over s squared plus 3 term, we would use a inverse Laplace transform equal to a sine of at, where again a is equal to the square root of 3. And with a little bit of manipulation here, we can then input this expression into the solution for y of t, which would be the inverse Laplace transform of y, capital Y of s. So now this pesky little thing, the inverse Laplace transform of g of s times 1 over s squared plus 3, well, we're gonna note here that we can, break things up again, this 1 over s squared plus 3 term, and we can express it using the square root of 3 here. But then we're going to use that nice little theorem involving the convolutions being equal to the product of the Laplace transform. So let's take a look here. The inverse Laplace transform of capital G is going to be lowercase g of t. And the inverse Laplace transform of that other piece, well, we know what that is. So putting this convolution theorem together to find the inverse Laplace transform, let's take a look at what that's going to look like all together here now. So the first 2 terms have the pieces we found earlier, and then the last term, we are going to be able to express that part as a convolution. A convolution is an integral, so our general formula for the answer to the solution of this will have to involve this integral, since we do not know what g of t initially was. And so at the end of the day, we get this long expression here to be our general solution to that differential equation with the given initial conditions that we were starting with. So that's a little taste of convolutions in the world of integrals and differential equations. But there are great videos out there talking about how convolutions are used for image processing. And you should definitely check out Grant Sanderson's 3 blue, 1 brown videos on convolutions. They're awesome. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.